I'm Bob Suma from Armstrong. I want to make a little bit of an apology before we get started because we're a little unprepared because there was a communication gap about this presentation. But the thing is that Paul Armstrong, one of the principals of our company, and myself got over 30 years each experience, so we can go through this. We've presented this stuff quite a bit. He's in the process now of looking for a presentation so we can show you some pictures. Paul's sitting down there with his computer. My understanding from reading what we're supposed to be talking about is alternative casting methods in aluminum, being graphite and plaster casting. I'm not quite sure exactly how much experience there is in the audience, so if I simplify it too much, just start waving at me and I'll step it up a notch. I'm not sure exactly how much experience you have in casting, but casting in plaster is similar to any kind of casting method where you're taking a substrate, in this case aluminum alloy, a variety of different alloys, and you're melting them down and putting them into a plaster and or a graphite impression. Plaster molding is basically done by making one part at a time. What they do is they take an engineering file. We take that file and we build shrink into it because the aluminum has a tendency to shrink to a certain capacity and certain dimensional based on the geometry of it. And so what happens is we build a mold, and what we do is it has a master tool. The master tool looks exactly like the part. There's an A and a B half that go together, just like a standard mold. What happens off of that is we pour a plaster into it, a rubber into it, and we duplicate it, then we duplicate it back again. So now we have a rubber mold that we run the plaster molds off of. When we fill that with a frame with plaster, the mold flexes as you strip the substrate off. Plaster is pulverized rock. It is not very flexible. It cracks easily. So what ends up happening is the mold flexes and the plaster does not crack. If the plaster cracks, when you pour aluminum into it, it has a tendency to break free. And of course, what happens is you have aluminum in places you don't need it. So what happens in plaster is you make one at a time. You strip them off after they're firm enough to move. When they're done, at the end of the day, you put them in an oven for X amount of hours at X amount of degrees to dry them. They have to be bone dry. What ends up happening is if they're not dry, the aluminum, which is about 1300 degrees F, when you pour it, will turn to steam immediately with any moisture, and you'll cause an explosion and everything goes kaboom and you have nothing. So drying is very important. Plaster is an insulator. The reason why that's important is that allows us in plaster mold to make very thin wall parts. We can make parts that emulate die casting steel dies very easily. We can run 80 thousandths, 60 thousandths, and in some cases 40 thousandths walls in certain geometries. The average wall is going to be somewhere between 80 and 120. So what happens is you put these two molds together, you can make cores and cavities. The nice thing about plaster is you can wash these things out when they're done. So I can make undercuts. I can make, for instance, I could theoretically make a bottle with an undercut on it, make a core inside, wash that core out, and have a bottle made out of aluminum. You couldn't do that in steel because you couldn't clear the core that would have to make the inside geometry. So what ends up happening is you have an A and a B half, one mold at a time, and you break it apart, throw it away, you repeat the process. What is it good for? It's good for prototypes because I can make my tools in approximately a week to 2 weeks. I end up making parts in about 2 to 3 weeks depending on complexity. And sometimes I'll make parts that take quite a bit longer because the geometry is harder, and they may take a lot more weeks where we might have 20 or 25 different cores to make very complex geometries. The advantage of it is it gives you good surface finishes, like an RMS finish in machining of approximately 62. That's kind of a standard finish, so it's very smooth. And the other advantage to it is that you can do undercuts in all kinds of geometries that you want. And what I do is I take the part later. Our main alloy in plaster is normally A356, as opposed to die casting, which is A380. I usually will add a secondary operation to that, the T6 heat treat it, to bring it up to a hardness so that it's easily machinable. So I can give you stuff that will perform just like a die casting. I can give it to you for 10 times less cost on the tooling, probably about 8 times more costly on the piece price. So if a tooling is 50 grand and die casting, it's about 5 for me. If the die cast part's 10 grand, it's $10, it's $100 for me. I get it to you in 2 to 3 weeks. They get it to you in 8, 10, 12, 14, depending on situation. So what it allows you to do is oftentimes we can make things that allow you to go to FDA approvals, testing, trade shows to show samples that actually work. You step it up from an SLA because you have an actual working model made out of the material that you actually test. So that allows a lot of our customers to come to us. And then what ends up happening is you can make an indefinite number of parts. Tooling, for instance, can be guaranteed for the life of the program because your master tool is sitting on the shelf. After you do this rubber urethane emulating of the part, the master sits on the shelf, never gets worn out. If the rubber ever gets worn out, you just make another pour and you have a tool back to day one. So when, for instance, we guarantee our tooling for the life of the program. So I could theoretically make you millions of pieces. You don't want to pay $100 a piece for a $10 part. That's usually the limiting factor. Now on the graphite side of things, for those of you that know injection molding and die casting, graphite casting is very similar in the sense that if you understand die casting, you have a hydraulic press, very robust, big platens, lots of high pressures and things of that nature. Graphite casting is somewhat similar in the sense that it's exactly like die casting, except it's a lot less robust. It's pneumatically run. We pour the alloy into the mold rather than shooting it under pressure. The molds are made out of graphite. Graphite is a chilling material. It pulls heat away. So you have some challenges on gating and fill parts. So we have minimum wall thicknesses of about 120. The good news about it is I can turn around and I can make a tool for $6, $7, $8, $9, $10,000, and I can make parts for $20, $30, $40, $50, $70. So that's kind of in between plaster and die casting, and I can make the tool in about 3 weeks. So it has a lot of advantages. The other advantage is I could run alloy 380 every day at all times, and therefore oftentimes on military or medical procedural projects where I have to get approvals and I need the same material, I can use the same material, get that material approved, and then when you go to die casting, you don't have to go through a second approval process. But it works exactly like die casting in the sense that you have undercut issues, you have slide issues, you have the same limits and the same parameters as you do. One good advantage of it is surface finish on graphite is actually better than die casting because of the way the surface finish it has heat taken away. It actually comes out smoother than die casting. So there is that alternative for people who want to have 50 pieces, 100 pieces, 500 pieces and don't want to spend $50,000 for a die. Come to me, they'll spend $8,000 for a die, I'll get them parts in 3 or 4 weeks. They'll just pay about 3 times more for them than they would for a die casting.